Hi everyone, and welcome to our second session with Brian Putt during the Risk Awareness Week. Make sure, even if you haven't watched the first session, we will do a quick recap in a second, but make sure you come back and watch the replay of the first session to kind of completely understand the whole decision journey. And what we're trying to do is we're trying to take a real life scenario situation, traveling to the airport, and we're trying to apply decision quality framework and quantitative risk analysis to that live decision and see what it will tell us. Because whenever we're faced with a lot of uncertainty, there's nothing better than trying to quantify that uncertainty and use that to make a decision. So now I wanted to hand over to Brian. Brian, maybe just for the sake of the people that are new and haven't seen your first session during the Risk Awareness Week, do you mind quickly introducing yourself, and then it's over to you to kind of recap on what we've talked about last time and continue with what we're going to do today.
Okay, thanks, Alex. Yes, I spent several decades working at Chevron and 25 years working in the field of decision analysis, and practicing it. And since retiring, I've been basically putting together mostly a YouTube channel that talked about probabilistic analysis and using SIPmath that is available from probability management.
Which is an important point, because just below this video, next to Brian's name, there's a link to the YouTube channel and there's a link to the probabilitymanagement.org where you can download the software for free that we will be using. Are we going to be using the functionality that is available in the free package of SIPmath?
No, some of the stuff is actually from the Enterprise version 4.0 that's been recently released and is available.
Yep.
It's I mean, not it's an advertisement, but it's only $500 versus thousands of dollars for some of the other Monte Carlo stuff. So exactly. It's a very reasonable price for what you're getting, and there's also some discounts that you can get by watching some of the other videos, I think. So get $150 off, in fact. So it'll only be $350. Anyway,
perfect.
So I think one of the purposes of this video, Alex, is to demonstrate the high functionality of this Enterprise 4.0, and we're going to be doing quite a bit of analysis today. I'd like to start with that review that you talked about. So if I might share my screen.
Yes, please.
And so this is the framing document that we had in our first session. And I was going to hit a couple of these worksheets, but you can see the frame document's got a number of worksheets down here. But this DQ spider. So in the first session, we talked about the frame. We did that really well. We got some really doable alternatives. And you initially gave me some rough estimates for some of the uncertainties as the subject matter expert. Because you have two roles, subject matter expert and decision executive in this particular case. Mm-hmm. But I think we need to review those because I had to make up some dumb numbers. So I'm expecting some changes when we review those inputs. Mm-hmm. And then we also need to check make sure that it's logically correct in the model. Because once again, I had to take those uncertainties and put them together. So we'll kind of quickly review some of that. And then I think the clear values and trade-offs is going to come through when we do the analysis. One of the key things I'd like to talk about is the strategy table, because we're going to actually solve the strategy table all at one time. We've got a number of different strategies, mm-hmm. and actually there's more than this that we ended up evaluating, or we're going to evaluate. But this helped us think through the different alternatives of what we wanted to look at. So let's turn over to the model now, okay? So Alex, here's our model. And as you can see, there are a number of variables here. These uncertainties we talked about, and we needed for those different scenarios we're going to evaluate. Mm-hmm. And I've organized them more by units than by, whether my wife drives, or you take a taxi or a bus or the train. Those are the four main strategies. So they're more by units. And then we have some common uncertainties down here. So what I like to do is start by going through each of these uncertainties and making sure I've interpreted the information you've already given me. First of all, I want to confirm that we're talking about a triangular distribution with a minimum, most likely, and max, and not something like a P10, 50, and 90 that you've given me.
Mm-hmm.
Okay, so that's correct. So let's just go down these really quick, like petrol costs ranging from 115 to 160, and I think this is the average of those two.
Yeah, the petrol cost seems fine. Liters per 100 kilometers seems fine. Parking rate, I think, is probably a little bit more expensive. It's a good point here that there's no minimum and maximum for rate per hour because it's a fixed fee. So we make all of the 3 points in the triangular distribution equal. But let's just, for the sake of the argument, let's make it €5 per hour.
€5, okay. All right.
And do you want to, just for the sake of our participants, do you want to quickly mention what RV and used will mean and how it's kind of taking a sample from the distribution for the sake of our future modeling?
Sure. So one of the advantages of SIPmath is it's really a tool. It's not like a crystal ball or at risk. It's a tool that helps you build the model. It doesn't actually run the model, if you will. SIPmath doesn't. So what you have up here is a formula for calculating the triangular distribution based on some random number, which is actually over here to the right. And then what I've done over here is simply said what value random variable do I want to use? And I've said just use this for the time being, because at some point in the analysis, you may have a reason that you don't want to use that random variable. You want to use something different.
Yeah, yeah.
So for example, if I wanted to at this point in time, I could just override the €5 and put a 3 in there, and then I could easily copy this back up. Okay, so that's the advantage of having that, because I wouldn't want to mess with this long equation up here.
Absolutely. I mean, we usually have that at work when we want to quickly switch between deterministic and stochastic model. So we need to have both, and we need to have a separate cell for the kind of the value that then later goes into the calculation that can become either stochastic or deterministic.
From a modeling perspective, when you say deterministic, what I would probably want to do is make everything most likely. And I'd probably have a switch, you see, that I could say, if there was a switch here for deterministic, we could put that in if you want, Alex. Yeah. Everything would just go to the most likely number.
Yeah. We won't do it for the sake of this exercise, but it's a good practice to check consistency and just check model logic to have the deterministic option to see it. So
I absolutely agree with that. Absolutely agree with that. Yeah.
Well, let's continue with our assumptions. So the next one is time to drive to the airport. Now, I think the kind of more realistic range would be somewhere between 90 minutes and 120 minutes.
Okay. 120. And then what is the most likely here?
And the average would be 100.
100. So, all right.
Well, sorry,
so a little bit skewed to the max. Yeah, it's a skewed distribution. It's not a symmetrical distribution now, right?
Yep.
Okay.
Which is fine, right? It doesn't affect.
That's fine. No, absolutely. Triangular distribution, it can be skewed. That's correct.
Okay, perfect. Time to train station is probably 20 to half an hour, 20 to 30. So 20, 25, 30.
Once again, skewed. No, this is symmetrical. Okay.
Yeah. And time to bus station is 5, 7, 10. Because it's much closer.
Connection time to the train. This is how long you have to wait for the train to arrive.
Yeah, that's actually probably 10 to 15 to 25. Time on metro and train excluding the connection between train and metro because we've modeled it separately. Yeah, that's probably accurate. Bus.
I'm on the bus. Hours.
Yeah, bus seems fine. Parking, I would say if it's in hours, maybe 0.5, 1.2. Or maybe if it's 0.5, 0.6, and 0.7.
Okay, it's fine to talk about these numbers, Alex. Can I ask you a question here? And we should tell our audience here that, hey, what we're doing here with Alex and chasing these numbers, we have not done before, so we have no idea what the answer is going to be. But I also have a logic question here.
Yep.
I think this time parked is your wife is driving you to the airport, and then she's going to park. Is she coming in with you, and you're going to take that time to get to the airport? Is that what's happening?
Yeah.
Okay. So she could just drop you off.
She could, yeah.
In this case, she's parking, going into the airport, getting you through security or whatever it is, and then leaving. Okay.
Yeah.
Right. So here we've got 20% chance she parks for you.
Yeah. So 20% of the time she would actually decide to park and kind of walk me to the plane. And then taxi cost is variable. And then tolls are probably variable as well. I mean, just for the sake of the argument, let's make it kind of 20, 22, 25, because theoretically different routes may have different number of paid roads. And then we have common uncertainties, and these are very interesting, and I think we will test them as we go through the model. But one of the very important things that we've decided to incorporate in the last workshop is that time has value for me. So we know that train and bus will take much longer than taxi and car, while being less expensive. But that extra time spent on the bus, it's not free, because I could have used that time for something more valuable. So for the time being, we're allocating a value to 1 hour of my time of 60 euros.
Traffic uncertainty.
Yep. So one of the risks that we're trying to kind of incorporate into the model is the how much uncertainty can traffic create for the journey time in minutes. And I think it would be a good estimate to say minus 20, because it is possible that roads are completely free. I mean, for example, coronavirus kind of gave a few examples when roads were much emptier than before. But it's still 120 kilometers, so you can't get there too fast.
Yeah. So right now the time to the airport is a minimum of 90.
Yeah. So
and you're saying I could save 20 minutes off of that.
Yeah, exactly. It's a pretty significant saving. And then 0 and 40 seems pretty fine. Risks. One is bad weather, and there's a 30% probability that weather will be bad. And if the weather is bad, it will probably have, I don't know, maybe -5 positive impact. So if for some reason, because of bad weather, drivers decided to stay home and the roads became freer than anticipated, it's unlikely, but that's why we will have a very skewed triangular distribution. But then the downside, which is in our case kind of the increase in the travel time, plus 30 minutes, that's quite plausible. And then the risk number one, if you remember from the last workshop, I don't drive. So one of the underlying assumptions is that my wife has to drive me. And then of course she's not always available. And if she's not available, I may be forced to take a taxi instead, to use the other modes of transport. we will put a probability of her being available to drive at 60%, which means 40% of the time she won't.
Okay. All right, so we're happy with all these inputs. It'd be really good practice. You've been giving me a lot of good reasons why these, why this was a -5 and this was a 30. It'd be really good to document those, either here in the model or in some other document, because you come back to this thing a month later and we say, well, why was it -5 and why was it 30? We have that documentation.
Yeah, that's actually a very good point. And in fact, for every model that I would normally do in the office, I would have an accompanying document which would list all the reasons for the range and the source of the information, because normally we actually have to make it auditable. And even though it may seem like I'm just guessing the numbers, that's actually not true. In between the first and this workshop, I've actually done a lot of research to literally calculate the number of kilometers, to check the prices, to check the possible distribution and the volatility of the time travel based on our experience. So there's normally a lot of work kind of that goes into those assumptions and the volatility around them. And documenting that is very, very important for decision making and auditing purposes.
Now let's talk about being logically correct and making sure we've got the right kind of numbers here. So if you think about the wife driving, she's got the time to the airport, which I think is just coming from the random variable up there. We'll go through one of these and then we can move the others faster. The impact of weather. Let me go to a different trial here.
Yes.
So we can see some probability of bad weather. So you can see weather came in here at this point in time, and the parking would come in if it was if she parked or not, right?
Yep.
But the point was that these numbers are changing. We have the traffic uncertainty, which in this case was, you can see the traffic is 4 minutes here.
Yep. There was some traffic, but very low, and she didn't.
Very low, yeah. It was, well, it was just a little bit less than the most likely, right?
Yeah.
It was a little bit higher than the most likely. And the parking time, we didn't park. So it took, in this particular case, it took 119 minutes for this particular trial for your wife to drive you to the airport.
Yep.
And then for the cost, you had to pay for the petrol getting to the airport. You had some tolls, 21 euros for tolls.
Mm-hmm.
Because we didn't park, there's no time for parking. Obviously, there's no parking cost. And then you have to value your time, right? So that was got 119 minutes at 60 euros an hour. So then we've gone through the other time to the train, time on the train and the metro, connection to the metro. Time on the metro, we said was already included on this one.
Mm-hmm.
So, and then we had the dead time from arriving too early. We decided to kind of leave that out of the analysis for the time being.
Yep.
So we got total time here of 192. And for the cost, we have the cost of the petrol to get to the train station. We have the train ticket, the metro ticket, and the value of time. Bus is car to the bus station. Time on the bus, bad weather impact on the bus.
Yep, because
traffic delay
and traffic affect buses in the same way as they would affect us driving.
Right. Obviously, did not have an impact on the train.
Yep, and obviously it doesn't on the train.
And then the taxi, got the time to the airport, which is going to be a little bit faster, I think. No parking involved there, but you have bad weather and traffic delays. And then you have the cost of the traffic and the cost of your time. That's what we have there. So we've got 4 different strategies, and we've really got 2 value measures. We've got the time to get there and then the cost. And these are things that are going to be played off against each other as you think about the alternatives available to you.
Mm-hmm.
So what I'd like to do is I would like to develop a strategy table. We want to do the strategy table here, and we want to have a clean PM table. So I'm going to save this current PM table and give it a new name. And I'm going to call this archive PM table, and I'm going to call it, archive it as model. All right? And what that did is it stored it away over here. It's not active because it's not yellow, and now we have a clean PM table. We're now ready to calculate both the time and the cost for all of our four strategies. So we have the wife drives, train, bus, and taxi for time, and then wife drives, train, taxi for cost. And then I have a reference over here, which is kind of where I want to leave my model when it kind of finishes doing this multiple experiment. And the way the multiple experiment is going to work is it's going to, just like the PM index cycles through the trials, it's going to cycle through these different cases. So let's put a case number here. I tend to use a 2 just to make sure I'm doing the right calculations. And we'll say this is equal to index of these things here, okay? And I need to put a comma 2 up here. And then this 2 I'm going to fix, F4 hit. Then I can copy this down. I guess there's just one to copy down. So it says time and train because it's a 2. And if I put in a 5 there, it would be cost and wife drives. Okay, see how that works?
Mm-hmm.
So now I want to know what value measure to use. Well, when the value measure that I want to capture says cost here, I want to capture the cost. When it says time, I want to capture the time. So I'm going to say equals if this equals time, then I want to capture my time to the airport.
Mm-hmm.
And if it's not equal to time, I'm going to capture the cost because there's only 2 options there. So right now, it's on option 5, case 5, and case 5 says cost. So this is a cost. This is not the time. It's cost 176 euros for my wife to drive you to the airport. Okay, now we're ready to calculate all of these cases.
Mm-hmm.
So what we'll do is we'll highlight the value measure, SIPmath, define outputs, and we're going to use multiple experiments. So multiple experiments is only available in the enterprise version, but it's really, really powerful because I'm going to give this a name of strategy and an input name. Oh, output now is this cell here. Input name, I'm going to use ME. It just stands for multiple experiments. It can really be anything you want. The input cell is this 5 because that's the variable I want to change from 1 to 9.
Mm-hmm.
And the input values for that are going to be 1 to 5, 1 to 9. And the spark lines, I like to put up here. You can put them anywhere you want, but I like to just put them up there because I like to know what things are actually the random variables.
Mm-hmm.
And I'm going to say OK. So it is doing 1,000 calculations for 9 things. Now, I don't know, you know what we didn't do is we didn't connect these. I'll tell you, I'm going to do something and then it'll become obvious that I didn't do it quite right yet. I'm going to take the average of these cells, and then use SIPmath get stats. The get stats will replace this M6 with a vector, okay? SIPmath get stats, and now it says strategy ME2. Now, I look at this and I say, oh my gosh, these are all the same. Something's wrong. I don't expect those all to be the same. And the answer is, strategy table, the wife drives has to come over to my wife drives. So let's say equals this, strategy table, wife drives. And now if I come back over my strategy table, I hope I get different answers. I get different answers now, okay? Which is what I expected. So there's a couple of things we can do here. One is we could calculate the, people talk about
further. Just for the sake of the people watching us, what we've just done is for each of the 4 modes, we've run a simulation in terms of the volatility of time, and then we've run 4 more simulations for the volatility of cost. And then in the row 10, you've just outputted the kind of the average time for wife driving, for the train, for the bus, for the taxi, and then the average costs for each of the modes.
Correct. So we might be interested in the uncertainty related to that. And, oftentimes they'll talk about standard deviation, but, most people don't understand standard deviation. And so what you might want to talk about is maybe the P80 confidence band, okay? So that would be going from the P10 to the P90. Does that sound a reasonable thing to do, Alex?
Yep.
Okay, you would understand that? Okay.
Which of the variables from the 10th
right.
to 50th percentile.
So to break this down into, and also we're going to need it for graphics, let's calculate the P10 down here. So that's going to be equal to the percentile of this variable in 0.1. Now I'm going to copy that across. So don't worry about the nums yet. And then we're going to do this once again, get stats. Remember, the get stats replaces those single cell references with vectors.
Yeah.
So now I've got the P10. Now the 80% confidence would be the P90 minus the P10, right?
Yes.
Okay. So let's say make this equal to the percentile of the same vector, but now we're going to use the 0.9. And then we're going to subtract this value. And once again, we'll copy this across. Don't worry about the nums yet. And we will then do get stats.
Interesting.
Okay.
So the volatility of driving taxi and bus is, in terms of time, is so much greater than train. So train is kind of more precise, easy to plan if we need to be there on a very specific time.
Yeah. So okay. So let me make sure I follow what you said. You're saying that the uncertainty, this 80% confidence band on the train, is very small relative to the driving with your wife, or the bus, or the taxi.
Yep.
That's a really good observation. Very good observation.
Which is kind of ironic, is that the 80% range is the highest on the wife. Because I have to go through the parking and say goodbyes, and there's also all this emotional time. And with the taxi just drops me off, and I run into the airport. Right.
That's right. And also remember that there's yes, that's true. Because we've said when the wife is not available, this includes the probability the wife is available. So sometimes you're actually taking the bus, or the taxi.
The taxi, yeah.
Yeah. And the taxi itself has an underlying uncertainty that's high.
Yep.
Relative to the train. So what could we do with this? Well, what if we generated I'll tell you what we're going to do, Alex. We're going to generate some graphs, and we'll come back and look at some completed graphs, okay?
It's a good idea. So for the sake of this presentation, we have already generated the graphs, just the kind of the skeletons of the graphs, but we don't have the up-to-date inputs, assumptions in our skeleton graph. So we need to copy the assumptions from this model, because we actually went through the assumptions and we changed them. We need to copy the assumptions from this model to the skeleton graph model and see what the what the graphs will look like.
Okay. Yeah, because we don't really know what they're going to look like at this point. Okay, so we're ready to switch here, Alex?
Yes, you need to copy from this model. Let's use this time productively. If you have any questions or thoughts, just please write in the comments underneath this this session.
Okay, so we're gonna copy these, and we'll then come over to our other model where we have some graphs, and we're going to paste in some numbers here, and I'm expecting this maybe for these to change.
Yep.
Wow, I think we went off the chart here, Alex.
Taxi disappeared somewhere. Oh yeah,
because, I think because I need to reset that. There we go. There's the taxi.
Yeah.
So now we have this active graph, and let's go over to our strategy table. And hopefully these are the same numbers. They should be that we saw before. And here you can see we've already put together some graphs. So let's look at the time to the airport. So I think, as you've already noted, the train has the smallest P10, P9. I guess these rows got reversed in this model.
Yeah,
that's fine.
But that's fine, yeah.
So it's small relative to the others, but it also has the highest time, and this gray line represents the mean.
Mm-hmm.
And so then on the cost side, wow, then certainly the wife drives is really high relative to the train, the bus, or the taxi.
And the reason for that is that we have in the model one of our assumptions: if the wife is not available, then I'm defaulting to taxi.
You're defaulting taxi, but she also parks,
yes,
which costs additional time, right? So we saw that the time for the wife is higher than the taxi. Yeah. So here's the uncertainty of the wife, cost for the wife, mm-hmm. And here's the uncertainty for the bus. We really wanted to compare that to the taxi. Is that what you wanted to do?
No, it's fine, because let's have a look at our cost versus time graph on the top right. And we can see that taxi on average is just a little bit quicker because it doesn't have this parking element, but it is much more expensive to use. So kind of the taxi is really out of the question unless wife is not available to drive. And then the train is cheaper than taxi, but it takes just so much time. So train is kind of out of the question as well, because the value of my time is important, and therefore train is kind of, you know, a less preferable option. But then wife and bus, this is where I think the trade-off will happen. Driving is more expensive but quicker, and catching a bus is less expensive but longer. And these S-curves at the bottom are kind of a nice representation of the two scenarios.
Yeah. So the other thing I'd like to point out here is that the bus dominates the train, because the bus has less time and also less cost.
Yes.
So now, if you knew there was bad weather because you're getting ready, whether you go to the bus or the train is a decision you can make in the morning, right? Or make it the night before. You get a forecast for the weather. If you knew the weather was going to be bad, you might then decide to take the train rather than the bus.
Yeah,
because we know the weather's going to impact the bus
scenarios. Because we can go back to the model tab and change some of the assumptions and see how the scenarios kind of change preferences or change change their spot.
So here's that same graph back here on the model tab.
Yep.
Right. And so let's go back here to this bad weather. We said there was a 30% chance. Here is where.
Let's assume there's a 70% chance or a 90% chance of bad weather.
90% chance of bad weather. Okay. So the bad weather didn't change the train, but it moved the wife and the others. We can undo that now. Let's just look at this is the cost versus time.
Yep.
See how that moved that? Yeah.
Surprisingly, because I would have thought that the worse the weather is, the more preferable the train is, but it looks like the other variables that affect the train kind of overall time and cost are so important that even the weather, because our impact of weather is only minus 5 minutes to 30 minutes, that effect of the weather by itself is not sufficient to make train more preferable to other options. So
right.
In a way, that's a good conclusion, because we may think intuitively, we may think that if the weather is bad, I better be safe and catch a train. But it looks like the saving of the train is not significant enough to make it a more favorable option, even if the weather is bad.
Yeah, but remember, Alex, you've also said that if the weather is bad, there is a chance it'll actually have a negative impact on the time. I could actually get there faster.
Yes, true.
So now I think if we change this to 60 minutes.
Yeah, the options are much closer now.
Yeah. I'll undo that. So one of the advantages of having this enterprise, or just using SIPmath, it's not really related to the enterprise at all, is the ability to work with the decision executive or the subject matter experts so they understand the sensitivity to their input variables.
Yeah, I mean, what we're showing right now is a perfect example, because I mean, if I wanted to have this conversation with my wife for real, I would literally show her this model and she could play with the numbers and see how that changes the decision. Because one of the key inputs, my guess is, one of the key variables is value of my time. So I arbitrarily valued my time as 60 euros an hour. But let's see if I, for example, was valuing it at 30 euros an hour, would that kind of change the decision?
Okay, so we're going to put a 30 in here now.
Yep.
So now the bus has become much cheaper and the train's much cheaper because they haven't incurred a cost for being on the being out there longer.
Yeah, yeah. The overall cost decreased, but it doesn't seem like the options, the order of the options have changed. The wife driving and the bus still seem like the preferred option.
Yeah, but you only get to make one decision, Alex. You have to do one or the other.
Yes.
The question becomes now for an additional, what is this? This looks like 155 and this is 120. So what is that, 35 minutes? For 35 minutes, would you be willing to save 50 euros, 60 euros?
60 euros, yeah. I mean, that's actually a very interesting way of putting it. Can we, just for the sake of the, well, actually, no, this is fine. So 35 minutes for 60 euros. And in one of our assumptions in the model is that value of my time is 30 euros an hour. So the saving of 35 minutes is costing me the same as 2 hours of my time, which actually seems like a pretty good deal.
Okay, those are the calculations that we could easily put over here on the strategy table to look at these differences between these things, you see. Because we have all the numbers, readily available to us.
Yep. Which is kind of interesting because when I initially looked at this, I thought, well, wife driving looks like a much preferred option because it has the lowest time while still kind of keeping the cost reasonable. But then in reality, and I mean, I think this is actually the lesson you taught me during the last Risk Awareness Week, when we converted the kind of the difference in time into money, and suddenly it became obvious that maybe cashing your bus is not such a bad idea. I mean, I hope my wife doesn't watch this video because then I'll have to catch the bus all the time. But yes, it's interesting how if what this basically means is that the bus will take 35 minutes longer on average. Again, all of this is on average. We still have to talk about the volatility because there's a big element of risk, and the bus may actually take much longer if the traffic is bad. And it takes us 35 minutes longer, but we save 60 euros, which is actually more valuable to me than 35 minutes, because 35 minutes only has the value of 15 euros, which is half of my hourly rate.
So from a time perspective, the bus takes 34 more minutes longer, but saves me 68 euros.
Yep.
Okay.
So, and to me,
based on the assumptions that we've put into the model.
Of course.
So if we put this back to 60, those numbers are going to change. You want to go there, or you want to just leave it at 30?
Yeah, let's do 60 and see how that changes. Okay. So our original setup was 60 euros per hour.
That was 60 euros. So the time didn't change. That was still 34, but now the delta is 51.
Yep. So now it still is more beneficial to catch the bus because the value of 34 minutes is 30 euros, or actually 34 euros, and I'm saving 51.
The cost divided by the hours, which are this, divided by 60. So it's costing you, and we get rid of the minus sign, right? So it's costing you 89, but you've only valued your time at 60.
Yep.
Yeah.
Which seems that the bus option is great. But there's an important caveat, and this is what I think Sam Savage would be proud of us talking about it now, is that this kind of discussion that we've just had for the last 10 minutes, this was averages. So on average, the bus would be more economically beneficial than wife driving. But then there are certain risks that may happen, and there's volatility associated with each one that may, for example, bus may have additional risks associated with traffic because it's actually going through a different route, because bus goes through a very dedicated bus route through the center of Barcelona, and it may have a different traffic volatility than us driving through the kind of the side roads.
There could be bus lanes too, right? So, but I think we're double counting here, Alex. I think to do this analysis, we really need to come over here and make this a 0. Okay. Now let's take the cost of your labor out of it altogether.
Yep.
And now it's saying that the delta is, wait to finish calculating, is 149.
Yeah, which is a big difference.
Yeah. So to take the bus, this is the bus minus the car. You'd have to value your time at 149. In fact, why don't we, to test that, let's put this at 149 and see what happens, right?
Yeah, well, yeah, but bus and driving has the same
cost.
equivalent cost, just different time. Very interesting. Shall we try another set of functionality within SIPmath and see if we can, if tornado diagram tells us anything, any additional insights?
Sure. Well, I think we've already set up the tornado diagram here. So let me switch to the tornado diagram.
Yep.
Now, because I'm sticking with the tornado diagram, but because it's going to be using the new inputs that we've already put into this model. Because I have so many uncertainties, I've got like, I think 26 uncertainties, I want to do a proper tornado chart. And so with the proper tornado chart, I've got all these variables, and I want these bars on a tornado chart to represent the P10 and the P90 of the distribution.
Mm-hmm.
Well, we don't have a P10 and P90 in our inputs. We have a minimum and a maximum. So most people would just use a minimum and a maximum and call it, oh, that's good. Well, no, we're going to actually do a P10 and a P90. And I think we actually put it down here. We've got this great big multiple experiments, similar to we did the strategy table, okay? We've got multiple experiments here, but here we're going the P10, and then further over here, we've got the P90s. The P90s going down here, right? So this strategy table is actually a proper strategy table with an 80% confidence between the two endpoints of here and here. So here's my wife driving, and whether my wife is, let me make this a little bit bigger. We don't need to see the whole tornado chart at one time.
Yep.
So when my wife drives, the probability of the wife being available is really one of the largest uncertainties. Weather impacts us, traffic uncertainty impacts us. Obviously, the bus ticket doesn't have any impact on our wife driving. None of these others have any impact. Frequency of parking, we made that a skewed distribution, so we see that skewedness here, and the time to drive to the airport is down here. So really what's really important here is the probability of the wife being available. Now, the other one we wanted to look at was the bus, right? So here's my wife being available had no impact.
Mm-hmm.
Whether that impact, traffic uncertainty is now really big. I think the scale on this tornado chart has changed. We could fix that if you wanted to, but we just need to recognize that. And the time on the bus. So these are all pretty symmetrical, aren't they? Other than the bad weather probability.
Yep. And well, because we've only made a couple of skewed distributions and everything else is symmetrical.
Yeah, so this is kind of a universal, this worksheet, the way it's set up is kind of universal and pulls from the strategy table, okay? Because I can, when I say a bus, it knows exactly what I mean by, okay, here's what the bus looks like.
Yeah.
Yeah.
I think you may have to switch back to the strategy because I just wanted to test one hypothesis.
Okay.
I wanted to set wife availability to 100%.
Okay, we'll switch back here to the strategy table.
Yep. So this is an important step we're doing because the way SIPmath operates, it actually creates a Monte Carlo simulation inside the Excel table using the data tables attached to the tabs, to the working tabs of our model, which opens up such an amazing opportunities for sharing the files, for opening the files on the mobile phone, and literally you can change the inputs and recalculate all the graphs on the mobile phone. I've actually tried.
Wow. Okay.
And that was pretty cool. But let's for this, just for testing, change in our assumptions wife availability to 100% and see how.
Okay, I just wanted to point out right now we had a value your time at 149. You want to put that back to?
Yeah, let's put it back to 60.
Put it back to 60. Okay. And you want to put the wife availability
As
to what?
100%. Yep.
100%. Oh, such a good wife.
And let's just change the bad weather to like 30%, because it's
30%.
It's Spain. Never 90% probability of bad weather.
I have to make a comment here, Alex, that I've done this kind of analysis with subject matter experts for a real project, and they say, well, what if this great thing happened? My wife was always available, right?
Yes.
And it comes out to be really, that's a great answer. That's our new reference case. That's our base case. Well, yeah, but the wife is not always subject matter expert or decision executive. She's not always available. She's got a life too. She's not going to cater to you all the time. So anyway, you got to be really careful about when doing all this that you don't get boxed into a corner where they've got a reference case that's really unrealistic.
That's a good point. That being said, it doesn't really change our fundamental decision. It looks like it's still train and taxi are still kind of outside of the efficient frontier, so to say, and bus and wife are the two options that we're trying to to consider, compare, and trade them off.
But you would always take the wife here using this chart. I think you need to use that other chart. Where do we have?
Actually, no, sorry, you are right. You are right. It looks like now, because because there's no taxi component on the wife journey, you can see on the cost of airport, the 80% confidence interval has shrank, and so there's less volatility on the cost, and that means wife driving actually becomes cheaper than catching a bus. And it saves time. So it's actually an optimum option all around.
Sure.
So all I have to do now is just convince wife to drive me all the time.
Well, I'm glad I could do this consulting work for you to come up with the obvious answer.
Yes. Yeah. And I mean, I hope everybody who's watching us appreciate this, that we've taken this kind of, childish example, although it's real life, and sometimes it's not obvious. We were discussing offline kind of different complications, because what we don't have in this model is that the bus actually goes only 3 times a day, and that means for the flight that I want to catch, there may be no bus available at all, and I may have to sometimes choose to fly on the following day or on the previous day and pay for the hotel at the destination to catch the bus, and if wife is unavailable. So the real life scenario is a little bit more complicated. There are kind of additional uncertainties on top of it, but for our kind of purpose of just presenting this quality decision-making framework in a live scenario, I mean, that I think worked quite well.
Yeah, that could actually drive you to the taxi solution if you've got to pay for a hotel room and everything else.
Yeah.
And then there's also the possibility the bus or the train gets you to the airport, 2 or 3 hours early, and so you incur another couple hours of your labor costs too.
Which is exactly it. And I mean, this is kind of one of the reasons why bus and train would normally be less preferable, because the time that you spent at the airport just idly sitting waiting for your flight is usually hours instead of an hour that you need normally. All right, well, wonderful. Thank you very much, Brian, for kind of walking us through this journey. Any final conclusions? Any summary thoughts?
No, I don't think so. I think we've covered a lot of material. Once again, I think the Enterprise 4.0 enables doing a lot of this analysis a lot faster, because you've got all the strategies together. You can generate multiple tornado charts. You don't have to have multiple models where you've got to if something changes, either in the logic or the inputs, I got to change it in multiple models, because I can't, with the free version of SIPmath, although it does a lot, you can't have the normal outputs and multiple experiments, and you certainly couldn't have several multiple experiments in one model. So yes, you can get it done with the free version, and so for those that are thinking about doing probabilistic analysis using a Monte Carlo, I think I would start with the free version, and that might be good for you for quite a while until you get really comfortable with it, and then you can go over to the enterprise version.
Yeah.
And please take a look at my YouTube channel. I think you said there was a link, going to be a link down below. And I think I've got over 90 videos there now. Some of them are case studies, others are just quickie things of how to use SIPmath. So appreciate the opportunity to talk to you and your audience here, Alex.
Thank you very much, Brian. And I'll see everyone in the other sessions during the Risk Awareness Week. And don't forget to ask Brian questions in the comments below. Thank you, and see you in the next sessions.